This video will discuss the friction lab and just kind of in general friction basics. This should be helpful if you're writing your second draft of the friction lab or if you're studying for the midterm. The sources of friction that we want to remember are surface roughness, force of contact, and not surface area. Surface area we determined does not have an effect. And through this video, we will talk about why that's the case. So first off, or I guess second off at this point, let's take a look at the data. This data here in this table is, quote unquote ideal data. It's the data that if we took the average of most students across the 8th grade, this is about what they would find. Your data might be slightly different. That's okay. What we're really interested in are the trends. What we see here for these first two is a slight decrease in the friction with the sandpaper block when it's on the long table and the countertop. And we see a big increase here. We see a massive increase for all of force of contact, and we see a doubling approximately for the wide blocks, for the surface area. This is all in comparison to the control. Remember, our control is our comparison. It's what you start with before you start adding in the independent variables, right? These are 3 separate independent variables that we test on their own. We test them against the smooth block to find out if there is a change, right? If there's a change from quote-unquote normal. So let's first talk about surface roughness. Why do we claim that surface roughness is a source of friction? Especially because for 2 of the instances, it actually went down. So surface roughness, if you're looking for a definition, we can't just say it's how rough a surface is, right? We would talk about the texture of the surface. We talk about the hills and the valleys. So in order for surface roughness to really have an effect, those hills and valleys need something to lock onto. There needs to be 2 rough surfaces. If instead you have a rough surface and a hard, smooth surface, like the long table or the countertop, what's going to happen is that sandpaper block or that rough surface is just going to kind of glide over the smooth one because there's only a few points of contact where it will actually be touching. So there will be nothing to dig into. It'll just glide right across. So that's why we saw this decrease right here. In contrast, when we were using the carpet in the sandpaper block, the carpet is very bumpy. It's also relatively soft. It's got, carpet is made up of not really hair anymore, but right, it's got all those fibers that stick up. So that is a very bumpy, textured surface that allows this to occur, where those hills and valleys will lock onto each other, they'll smash into each other, and you have to force it over each other. So that's why surface roughness goes up. If we're going to look at force of contact, why does force of contact increase friction? So one thing that we need to be careful of is that force of contact is not just more mass. Force of contact is how hard you push 2 objects together. How hard objects are pushed together. So what that means is when you push those 2 objects together, if you've got a surface with some bumps over here, a surface with bumps over here, they're not touching anymore, right? There's no contact between them right in here. But if I push on this surface and I push on this surface, those small hills and valleys are going to get closer and closer together until they're rubbing. And even if they're tiny hills and valleys, the harder I push them together, the more contact there will be, the more rubbing that there will be, and the more that you then have to smash through the other hills and valleys to get those 2 surfaces to move. So one way that we can increase force of contact is just by increasing the weight of the objects. The heavier an object is, the more gravity is pulling it down onto the floor. Right? If you're trying to drag a really heavy object, you are dealing with not only the mass of that object, but you're dealing with how hard that object is getting smashed into the texture of the carpet or the linoleum floor or whatever kind of, the dirt, whatever you're moving it over. So this is a very important piece here. That if we have a 10 kilogram box, right, and it's on the floor, if we were in a frictionless world and we wanted to accelerate this box to 5 meters per second squared, that box, no matter what, would take 50 newtons of force, right? 10 times 5. And if we had a box that only weighed 1 kilogram and we also wanted to accelerate it to 5 meters per second squared, this box that has less mass would only take 5 newtons of force to accelerate it to 5 meters per second squared. That's not due to force of contact. That's just due to the difference in their masses. If we want to talk about force of contact, we're talking about in addition to the 50 newtons that it would take to accelerate this box to 5 meters per second squared, we're also talking about the weight that is pulling down due to gravity and making this box and this surface texture, this surface roughness, closer together. So the hills and valleys are now closer. Those hills and valleys are now slamming into each other more. So in addition to the 50 newtons just inherent to the mass, we now also have to deal with the friction due to the surface roughness and the force of contact, because that box is being pushed down onto whatever object this is, or whatever floor this is, rather. This 1 kilogram box will also have some force of contact, but less force of contact because its weight is smaller. Finally, can we claim that force of contact is more important than surface roughness? The answer to that is no. We cannot claim that. While our numbers went up a lot more than for surface roughness, that's because of something that we call the treatment amount. So the treatment amount is how much of the independent variable you apply when you're doing testing. When we were doing the sandpaper block, the sandpaper versus the smooth block was a little bit rougher. When we changed to the carpet versus the table was a bit rougher. So we changed the roughness, but not by a lot. We changed surface roughness a little, right? We don't know exactly how much, but not by a ton. When we added on that large block, we added on a large block that was about 600 grams, and the smooth block was 100 grams. So we went from 100 grams to 700 grams. We changed the force of contact 7 times. So that means that the treatment amount here, the amount that we changed the independent variable, here might have been, 2 to 3 times. And here, it was 7 times. So we changed the independent variable a lot more, so we should expect to see bigger numbers. What we see is that when we change surface roughness significantly, the numbers go up. When we change force of contact significantly, the numbers go up. So for us, all we can determine is that in this lab with these materials and all the changes that we made, sure, we saw a bigger change for force of contact. But that doesn't mean that force of contact is more important or a bigger variable when determining friction. It just means that in our lab, because of the changes that we made and because of the treatment amount, we saw a bigger effect. That doesn't mean that in the world, force of contact is more important than surface roughness. So finally, we get to surface area, the one that had no effect. So at first, we should look at this and be like, okay, we've got 0.25 newtons over here, and we've got 0.5 newtons over here. That means it's doubled. So if the numbers doubled, why can't we claim that it increases friction? The numbers went up. Well, we need to remember that inherent to this lab is a built-in error, an error that I built in on purpose. We went from 1 block to 2 blocks. And by doubling the number of blocks, right, 2 times the blocks, you should have 2 times the mass. So if you're having double the mass, it's a situation like we're talking about here. It's going to take double the force to get that mass to move, right? If you have a 5 kilogram box or a 10 kilogram box, even in a frictionless world, that 5 kilogram box will be much easier to accelerate than the 10 kilogram box, just inherent to its mass. It's like trying to throw a tennis ball versus a baseball. The baseball takes more force, right? Or comparing a baseball to a bowling ball, right? So what we're seeing here is that double the mass requires double the force to get it moving. That's what we learned when we studied F equals m times a. If you increase the mass and you want it to keep accelerating, you have to increase your force. You have to push harder. So even though we know that surface area does not have an effect, if there's more contact, and contact is inherent to friction, shouldn't there be more friction? Right? Our whole definition of friction comes from the idea that if you increase contact, either through surface roughness or through force of contact, you're going to get more friction. So if surface area increases contact, why doesn't it create more friction? So to answer that, we can think of a brick, right? So here's a brick standing up, here's a brick lying down. Let's pretend for a moment that they're exactly the same dimensions, they're exactly the same mass, okay? So if they're on the ground, we've got this 1 kilogram brick pushing down with this area right here onto the ground. Here, we've got a 1 kilogram brick pushing down with all of this area onto the ground. So what we see here is that this one, there is more contact, increase of contact, compared to this one where there's a decrease of contact. So just looking at that, you would think, okay, this one right here should be harder to move because there's more friction. In fact, that's not the case, because while the contact has gone up, there's less pressure. And remember, pressure, like we talked about in class, is just force divided by area, meaning that there's less force on every single point where it's touching the ground, right? So whereas this 1 kilogram object has, these points of contact, there's fewer points of contact, there's more pressure on each of those points of contact. So there's a trade-off here. If you decrease your contact, your points of contact, you're increasing your pressure. Here you increase your contact but decrease your pressure, and therefore friction stays the same. It's like in class when we were looking at those images of the bed of nails and how people can walk across a bed of nails or lie across a bed of nails, but you can't walk or lie down on one nail. And that's because all of your weight, all of your force due to gravity, would be pushed down on that singular nail versus your entire weight being spread out over 1,000 nails, right? You can lie down on 1,000, but not one. So it's the same exact idea here where you're spreading out the mass when you're spreading out and increasing the contact. So this is why surface area does not have an effect, right? Even though we saw the numbers double. Take a look through this video. Come and talk to me if you've got any questions before turning in your friction lab draft number 2. Thank you.